Okay, yeah, welcome to the second talk of our session. Our speaker is Alan Liu from MIT, and he's going to talk about optimal state learning with any amount of entanglement. Take it away.
Okay, yeah, thanks for the introduction. So yeah, this is based on joint work with Sitan, Chen, and Jerry Lee. Okay. So let me get started then. So quantum state tomography is perhaps the most basic problem in quantum learning. So in quantum state tomography, there is some unknown state rho, which we think of as, say, a d by d matrix.
Sorry. For your clicker.
Here, I'm gonna.
This?
Not that one.
No.
Not that one.
Oh, okay.
There we go. It's working.
Okay, thanks.
Sorry about that.
So in quantum state tomography, you have some unknown state rho, which you think of as a d by d matrix. Okay, and then so you're given some copies of rho, and you can make measurements on these copies that you're given. Okay? And at the end of the day, your goal is to learn a description of some quantum state, say rho hat, that is close to rho. Okay? So this is quantum state tomography. And so there are a few obvious resource considerations in quantum state tomography. Perhaps the most obvious one is you want to kind of minimize the number of copies of rho that you actually need to measure. So this is important because, say, obtaining fresh copies may be difficult or expensive. Okay? But this is not the only important consideration. And so in particular, you also, especially on near-term quantum devices, you want to design a protocol that is also easy to implement. And so in particular, one important constraint of near-term devices is that they have limited quantum memory. So in particular, you can only make entangled measurements over, say, a limited number, say, t copies of the state at a time. And so this then leads to the natural question, sort of how do these near-term device constraints, namely this constraint on sort of the limits on quantum memory, affect the complexity of quantum state learning? So we should take the perspective that sort of both fresh copies and entanglement are actually resources. And so this is important because sort of as we develop better quantum devices, we may be able to run more complex but copy-efficient protocols. And so thus, perhaps more concretely, the question that we really want to understand is, can we sort of trade off between entanglement and copies? For instance, can we save copies by using more entanglement in our measurements? So of course, both entanglement and copies have been considerations that have been explored in kind of the vast literature on quantum state tomography, but yet we have a very limited understanding of sort of the interplay between these two kind of important axes. So now let me introduce maybe the more formal measurement and learning model. So we imagine that our learner makes measurements on sort of t entangled copies of the state at a time. So we make a measurement on this sort of t entangled state rho tensor to the t. And so the learner interacts with the state through the usual measurement model of a POVM. So the learner can choose some collection of PSD matrices that sum to identity in this sort of d to the t dimensional space. And then when they measure the state, they observe some outcome z with probability equal to sort of the trace inner product between the t entangled state and sort of the corresponding POVM element m sub z. Okay? So this is the usual quantum measurement formalism. And then we can sort of formalize sort of the way in which the learner, or sort of the full learning algorithm. So a learner that makes t-entangled measurements works as follows. So they choose, say, their first POVM m sub 1. They measure one batch of t-entangled copies, and they obtain some outcome. And then potentially adaptively, based on this outcome, they can choose a second measurement, measure a second batch, and then so on. And so they do this for a total of n over t iterations, so they use a total of n copies of rho. And so the main question that we'll seek to answer is, say for a given value of t, we want to learn some unknown quantum state rho to, say, some epsilon accuracy in trace distance using t-entangled measurements. And so how many copies n do we actually need? So I think this is a nice question because we, in general, seem to have a very limited understanding of sort of how to make or like how to leverage the power of entangled measurements. But of course, this is an important consideration as we try to scale up our quantum devices. So, sorry. Okay, so there's been a lot of previous work on quantum state tomography, but perhaps the bottom line is that previous work kind of addresses only the two extremes of t is equal to 1 and t is equal to n. So the t is equal to n extreme corresponds to sort of fully entangled measurements. So you make like a fully entangled measurement over all of your copies simultaneously. So in this regime, it is known, based on these works, that the right answer here is basically n is d squared over epsilon squared. And also in the sort of other extreme, the t is equal to 1 extreme, so this corresponds to basically single copy or unentangled measurements. So you measure your copies one at a time. So in this regime, the answer is also known, and it is known that the answer is sort of d cubed over epsilon squared. But essentially nothing was known between these two extremes, even for, say, t is equal to 2. So perhaps there's some fundamental reasons why we know like very little in kind of this intermediate regime. Sort of the reason is kind of the two approaches in the sort of t is equal to 1 and t is equal to n regime are kind of fundamentally incompatible. Okay? And what I mean by this is sort of the approaches for fully entangled measurements kind of work as follows. So you make basically this kind of like one-shot algorithm where you make a single measurement on all of your copies simultaneously, and then based on the outcome of this measurement, you construct some biased estimator for the state rho. But you show that when your number of copies is sufficiently large, then the bias is small. Okay? So these are kind of like one-shot algorithms. On the other hand, sort of the approaches for using unentangled measurements, these algorithms kind of average many copies of a single sort of a noisy but unbiased estimator. Okay? So for instance, for single copy measurements, you like have some very noisy estimate, but it's unbiased, and you average it over all of your copies. Okay? But to sort of understand the intermediate regime, you kind of want to be able to aggregate your information over sort of n over t different batches, but it is not clear how to do so without an unbiased estimator. Okay? So there's this kind of like fundamental incompatibility in trying to sort of like mesh the two approaches together. Okay? And okay, so this leads us to ask the question, could there be a smooth trade-off? Or so sort of as t grows, is there a smooth trade-off in the sample complexity? Or could there be a hard phase transition where sort of entanglement may only help at a certain point? And towards understanding this question, one important theme will be sort of how can we kind of reason about these sort of intermediate levels of entanglement? Like can we develop new techniques to kind of resolve the incompatibility between these existing approaches? Okay, so our main result is we give a smooth and optimal trade-off for many parameter regimes. Okay? And so to our knowledge, this is the first kind of smooth trade-off between entanglement and copies for any natural quantum learning task. Okay? So formally, our result is stated here. So for basically when t is like relatively small, we have upper and lower bounds that match, and we show that the answer is basically d cubed over root t times epsilon squared. Okay? So now let me take a minute to sort of interpret sort of the various regimes for this result. So the first thing to note is basically when epsilon is sufficiently small, then sort of our upper and lower bounds fully characterize the trade-off. So we recover the existing rates when t is equal to 1 and t is equal to t squared. And we also like smoothly interpolate between them. Okay? And in fact, our results actually give some improvement even for the fully entangled regime. So we actually show that sort of you never need more than t is equal to d squared entanglement, whereas previous algorithms actually use sort of d squared over epsilon squared entangled copies. Okay? And also, even in the constant epsilon regime, we also get a non-trivial improvement in the upper bound. Okay? And so we conjecture that sort of this d cubed over root t epsilon squared rate is actually optimal in this regime as well. Okay, so now let me try to give a little bit of insight into the algorithmic ideas. Okay? So recall that sort of the main theme is sort of how can we reason about these like intermediate levels of entanglement. Okay? And so we'll develop a sort of two-step algorithmic framework that gives us sort of a clean way to reason about sort of these partially or like limited entanglement measurements. Okay? So there are two steps. So first, we'll understand the case when the state rho is close to maximally mixed. Okay? So when it's somewhat close to identity over D. Okay? And then we'll give give a general reduction for reducing to the balance, what we call the balance case. Okay? So within the balance case, there are sort of two important steps. So the first is we'll show how to design an estimator with small bias when rho is kind of close to balance. Okay? And then once we design this estimator with small bias, we'll show how to bound the signal to noise ratio with some representation theory. So at a high level, our approach is, so we design an estimator with small bias from measuring a single batch of T copies, and then we'll average our estimator over sort of all n over T batches. Okay? And so recall what is the measurement formalism. So we measure like one T entangled batch with our POVM, and we obtain some outcome M sub C, right, which is d to the T by d to the T matrix. And then our estimator basically maps this outcome to an estimate for rho. So it maps this outcome, this like d to the T by d to the T matrix M sub C, to our estimate rho, or to our estimate for rho, which is a d by d matrix. Okay? And so we can kind of explicitly compute the mean of our estimator. So it's just basically the average over the possible outcomes of your POVM of your estimator weighted by the probability of the given outcome, right? And the probability of the given outcome is given by this inner product in the red. Okay? And so now it will be important to sort of better understand this like probability, this quantity in the red. Okay, so sort of the main difficulty with this expression here, this inner product, is that it is like kind of very high degree in the state rho. It is like a degree T polynomial in the state rho. And thus it is kind of difficult to construct like unbiased estimators because of this kind of complex like high degree polynomial. And so what we'll do is we'll actually show how to replace it with sort of a simpler, basically linear expression. Okay? So let rho be identity over D plus some small error. Okay? And then the idea is that when this error is small, we can approximate this rho tensor to the T with the first order, basically the first order truncation of this expansion. So specifically, if we just like expand this expression with like binomial theorem, we just take the first, truncate all but the first order term. Okay? So let the sort of first order like linear approximation be rho sub T. Okay? And now the main point here is that when the error E is small, then sort of we can, this approximation is good. So we can approximate this kind of T entangled state rho tensor to the T with this linear approximation rho sub T. Okay? This linear approximation is, well, because it is linear, it is sort of easy to design an unbiased estimator once we've sort of replaced the like high degree like rho tensor to the T with this linear approximation. Okay, so once we like do this linear approximation, we can design an unbiased estimator, but we still need to bound the signal to noise ratio of our estimator. Okay? So recall what are we doing? So we have our estimator, which is like given by this function f that maps our outcome to our estimate. Okay? And so then we replace the like rho tensor to the T with the linear approximation. Okay? And then because sort of rho sub T is linear in rho, we can replace the inner product with this expression in the red. So here, this expression in the red, sort of the folded version of M sub Z is just some explicit linear function of the entries of M sub Z. Okay, it's just like some explicit linear function of its entries. Okay, and so this is true just because rho sub T is linear in rho. Okay? And so now you can maybe do some computations. So you do some explicit computations, and you can get that the signal to noise ratio is given by basically this sum shown here. It's basically a sum over the elements of your POVM of this squared Frobenius norm of this kind of folded matrix. Okay? And so now, basically designing the optimal POVM and kind of like optimizing the signal to noise ratio basically reduces to optimizing this specific quantity that we showed on the previous slide. Okay? So for simplicity, assume that all of the elements of your POVM have trace 1. Then basically you just need to design a POVM that maximizes this quantity Q, which is the sum over the elements in your POVM of this squared Frobenius norm of this kind of like folded matrix. And to sort of understand or bound this quantity, there's one important lemma from representation theory. So roughly, we can relate the squared Frobenius norm of this folded matrix to various subspaces corresponding to partitions of T via some representation theory. So in particular, we have this theorem called Schur-Weil duality that gives a canonical decomposition of the space, the D to the T dimensional space, as a direct sum of subspaces corresponding to partitions of T into at most D parts. Okay? So this is we're writing this D to the T dimensional space as a direct sum of a bunch of subspaces. Okay? And each subspace is indexed by a partition lambda that is a partition of T with at most D parts. Okay? So this is like a canonical decomposition. And then the lemma basically relates the squared Frobenius norm of this folded matrix to the projections of the matrix onto these various what are called Schur subspaces. Okay? So this lemma is an inequality, so it sort of bounds the Frobenius norm in one direction by this kind of weighted average of the projections of M sub z onto these various Schur subspaces. But there also exists a POVM that achieves equality in this lemma. Sort of this POVM that achieves equality sort of guides the design of the actual POVM for our measurements. Okay? So we'll use the POVM that achieves equality in this key lemma. Okay? And so then we can go back and so recall we want to bound the signal to noise ratio. And so for the POVM that achieves equality in this lemma, in the key lemma, we just substitute into the above. And then we can change the order of summations for the two sums. And then the point is, because M sub z is a POVM, sort of the sum over all elements of your POVM of this projection is just the dimension of the subspace. And so the sum is just equal to, now the expression on the right-hand side no longer has any dependence on the POVM. It is just this sum over the dimensions of these various subspaces. Okay? And so the right-hand side is basically just some statistic about random partitions of T drawn from something called the Schur-Weil distribution. Okay? You can explicitly compute the statistic and show that basically the statistic on the right-hand side scales as T to the 1.5. Okay? Yeah. Okay? And so the intuition for this is roughly a typical partition of T roughly has square root T parts of size square root T. Okay? So you can explicitly compute this. And so if you substitute everything back, you get the sample, the desired sample complexity of D cubed over root T epsilon squared. Okay, so finally, as I alluded to earlier, there was a second step, which is reducing from the general case to sort of this balanced case when rho is close to maximally mixed, right? And okay, so there are a few steps in this reduction. So let me very briefly explain this reduction. Okay, so basically in this reduction, we'll transform our state into a different state that is close to balance, and also such that we can simulate measurement access to copies of this different state, this split state, through the measurement access to the copies of rho that we're given. Okay? So we'll basically simulate measurement access to this state, split of rho that is close to balance. And the way we do this splitting is, so then we can basically run our learning algorithm pretending that the unknown state is actually the split state, and then argue that once we estimate the split state, we can sort of back out an estimate of our original state rho. And so the way our splitting algorithm works is, so we obtain a rough estimate for rho, say using unentangled measurements, and then we approximately diagonalize it, right? And then basically looking at the eigenvalues on the diagonal, we basically split up the large eigenvalues by sort of duplicating those rows and columns to make those, basically split up the large eigenvalues and make them smaller. And then this will basically let us split up the state so that it becomes roughly balanced. Okay, so finally let me conclude by remarking about a few additional consequences. So I guess I presented this kind of general algorithmic framework for understanding the power of this kind of limited entangled measurements. So our framework also has some natural implications for some other quantum learning tasks. So in particular, for this task of shadow tomography, where instead of estimating the whole state, you just want to estimate some observable values to some epsilon accuracy, we also give an sort of similar looking trade-off for this task. And perhaps the important thing to note for this theorem is basically when epsilon is sufficiently small, we actually recover sort of the rate like log m over epsilon squared, which is the same rate as in the classical setting. Okay? And so I guess for this task of shadow tomography, it has been like a long-standing open question about whether you can actually match this classical rate of log m over epsilon squared. And the current state-of-the-art bounds in general are like not quite there. So at least we show that in the sort of small epsilon regime, we can actually get all the way down to matching this classical limit. Okay, and I'll also remark that sort of our algorithm even solves the harder task of classical shadows in that sort of the measurements we make are kind of oblivious to what the observables we need to estimate are. Now, okay, finally, let me conclude with a quick summary. So we give a general framework for leveraging partially entangled measurements for quantum state learning. So we give a smooth and optimal trade-off in many regimes for state tomography, and also an algorithm for shadow tomography that matches kind of this classical limit for sufficiently small epsilon. Okay? And conclude there. Thank you.
How crucial is trace distance in all of these arguments? Do you think you could do this for infidelity or something like that?
I think trace distance is not super crucial. I think, okay, it depends on for tomography, I think you can do it in, so at least for the balance case, you keep track of everything in Frobenius norm, and then you convert to trace distance at the end. I think fidelity maybe is a bit different because it is maybe more sensitive to small eigenvalues or something. So I'm not sure about fidelity specifically. Yeah.
Yeah, it's interesting that you work so much in Frobenius distance because you can sort of reduce Frobenius. Maybe we can talk later.
Yeah.
Okay, I actually have a question.
Yeah.
So you think about entanglement between the copies. Have you also thought about the other direction of only allowing a little bit of entanglement between the qubits? So, for example, in the other extreme, you only have single qubit measurements. And in principle, you can still do full tomography, but it will just require more copies, I assume.
Yeah.
Is that?
Wait, sorry, what is the question you're?
Oh no, have you thought about this? Are there any results in this direction? Do you know what the sample complexity for single qubit measurements is?
Sorry, I think I didn't quite understand the question. So you're saying, can you just repeat the question again?
Yeah, okay. You were thinking about single copy measurements versus entangled measurements across the copies.
Yes.
But you could also start with single copy measurements. These are entangled measurements on the copies. But you can also do something like single qubit measurements only.
Oh, I see. Okay.
And then you can still do tomography, but it will require more copies.
Yeah.
I was wondering if there's some known trade-off in that direction.
I'm not sure.
Okay.
I need to check the literature.
Yeah.
Okay. I have a question. Okay.
Can I ask a question?
Maybe first, before asking, related to Jonas' question, maybe Angus here, I have some work about single qubit Pauli measurements. Single qubit measurement, maybe a lower bound for a non-adaptive setting, maybe that D4 is optimal, maybe. Yeah. And my question is, okay, you showed a smooth transition, from D cube single qubit D square full entanglement for mixed state.
Yeah.
Can you show a smooth transition as well for bounded rank states?
I think for pure states, there is no transition. You can get the right rate with unentangled measurements, right? I think you can get, for pure states, we can get D over epsilon squared, which is the right answer with unentangled, right? But I think, that's a good question. I guess for intermediate rank, you can ask the same question of whether there is a similar trade-off. And I don't know the answer now.
Can you comment on the running time for the shadow tomography part?
Running time for, the running time is not good, I think, because I think all of these kind of like representation theory based things where you do this like Schur subspaces are, at least I don't know how to implement them efficiently. Yeah.
So it's polynomial. It's exponential.
Yeah.
Okay. Hi. Thank you very much for the nice talk and for the nice result. I would like to ask if you considered the task of like if these tools can be applied to the task of like LOCC tomography. I think that it's a related question to Jonas, the question of Jonas. I mean, if you consider, for example, D that is 2 to the power of n and QDIT systems, and you ask, for example, that you want to do just local measurements on, for example, each qubits and classical communications between each qubit. Or also, for example, it would be interesting the question of just two parties. I mean, just n half qubits of Alice and n half qubits to Bob. And what is the optimal sample complexity of learning bipartite states via LOCC?
Yeah, I mean, it sounds like an interesting question, but I don't know if I have any like concrete like answers or like ideas for how to like port the ideas over now.
Thanks.
All right, let's thank the speaker again.